Hello all, this is Kaushalam Shastri and I'm currently pursuing my undergraduation in from Bangalore Institute of Technology. And today I will be giving you an overview or giving you complete details of what is analog to digital converters. So let us go into the details of it. Let us look at the basic understanding of what is an analog signal. An analog signal is a continuous signal for which the time varying feature of the signal is a representation of some other time varying quantity. See, analog signal is nothing but the real world signals like pressure, temperature, voltage, current. So these are in analog form. In order to process them, we need ADC, that is analog to digital converters. So that we cannot, as you know, that we cannot, process it in analog form. We have to convert it in binary or digital form. So that's why we use an ADC. It's just the process of ADC is just to convert analog form into digital form. So this is a small understanding, a small picture which is supported, and you can see here that this is the voltage input, which can be anything, and the output is your digital signal. Okay. So next, there are some few technical terms, or there are a few processes which are involved in ADC, and let us look into it one by one. The first one is called sampling. Sampling is the process that taking and we have to take a analog signal and we have to convert it into discrete numbers of signal. As you know that analog signal is in continuous form, we have to process it, we have to convert it into discrete signals. Okay. From in here, there's another term called a sampling frequency, that how it defines that how many it is, it defines that how many times per second the signal will be sampled. Okay. So this is a very important term, because in order to process it, we use this term in the next theorem, a very important theorem, Nyquist theorem. Nyquist Shannon was a German scientist who gave the theorem stating that Fs is equal to 2 times of F max. Fs is nothing but the sampled frequency, and F max is nothing but the frequency of the input signal, that is the analog signal. If this condition satisfies, then we can have the most accurate reconstructed wave when we cut it down into a number of discrete values. And here we come across a word called as aliasing. So this aliasing will take up in the coming slides, but just to give you an overall understanding, alias is nothing but the error or distortion which it would have acquired from the surroundings. Okay, so this is the two diagrams which I have shown you here. You can see that just a minute here. This is the left one. You can see that the number of sampling rates is very less. There is only 5 points. So that so what happens here is that the reconstructed wave is not more accurate. But in the right diagram, you can see that the sampling rates are high, the sampling frequency is high, so that we can have a better what you can call better reconstructed wave. Okay, so next thing we go into what is known as quantization. Quantization is nothing but this is one of the process in ADC where the main function of quantization is to convert the amplitude from continuous into discrete. You know that analog is in continuous form and we have to convert it into discrete values. Quantization comes in various levels depending upon the n bit ADC, like 8-bit, 16-bit and 24-bit. 8-bit or 24-bit, and depending upon the requirement we choose the depending on the equal length. Okay, then the next things which we had already come across this term in the previous slide is called aliasing. Aliasing is the distortion which may have occurred during the collection of the analog signal. Okay, it may be sound waves, unnecessary high frequencies. So in order to reduce this, we have to reduce this because we need a more accurate data to convert it to discrete digital signal. So for that purpose, we use an anti-aliasing filter. This filter's main job is to remove all high frequency content from the signal which we have acquired. The anti-aliasing filter is nothing but a low pass filter, and there's a the frequency will be allowed only if it is equal to or greater than 2 times of the input, the frequency of the input signal. So this is the basic condition for it to allow. Okay, this is same as that of the polarization which we see in the physics concept. Okay, physics concept. Next block, we can see next portion we can see it as sample and hold circuit. The sample and hold circuit is basically we can already infer from the name itself, is just holding the signal. As we require the data for quantization and the encoder, we need some device. We need to have the signal to be at a constant state. We don't want it to be changing over a multiple times. So that's why we use this sample and hold circuit. The last and the final block or the process which comes in ADC is nothing but the encoder. This is the main logic or the main crux of ADC. So encoder is nothing but the signals which would have been passed from the anti-aliasing filter reaches the encoder, and then the encoder gets converted. In the encoder, the analog is converted into digital signal. So all these are just these four processes are very important, so that we get an overall view from it. Okay. Yeah. This is the overall view that I had to. Sorry. Sorry. Here you can see the overall view, and I have given the diagram that we have a sampling block, we have the sample and hold circuit, we have the quantization block, and the last we have the encoder. This is the overall understanding of the conversion from analog to digital in the analog to digital converter. Okay, you can see here that in the initial part the analog was continuous in time and continuous in amplitude, but at the last, from the encoder, the output is discrete in time and discrete in amplitude, and that is the overall concept of analog to digital converters. Okay, it is very simple. Okay, so let's go move on to the types of ADC. The first one is the flash bar comparator converter. This ADC is also called as the parallel ADC. This type of ADCs are mostly used where the requirement is in terms of speed, and accuracy is very less. It is less compared to the other ADCs, but this is more fast. So let us look into the diagram so that we can get a proper an understanding of what is a flash bar comparator converter. As from the name, we see that from the name of the converter, we see that comparator. So the main logic of this, what you call, is the comparator. Is the comparator itself. Here we know that the working of the comparator, that we have the non-inverting terminal, which is indicated by the plus. We have inverting terminal, that is indicated by negative. The main function of the comparator we know. So here what we are doing is that we are comparing the voltage input voltage at the non-inverting comparator with the inverting comparator. So what we do here, we are comparing here. So the output of the comparator is being given to the priority encoder, from which it is successfully converted to digital signal. Here this is a 2-bit comparator where 2 to the power of 2 is nothing but 4. So as you can see in the V reference, where we have the resistors, we have 0, V by 4, 2V by 4. Like the same way, we can have it for n-bit ADC. We can have it for 8, we can have it for 4. In case of, if there are 8 comparators, then the V reference starts like 0, V reference by 8, and 2V reference by 8, 3V reference by 8, like that. But this is a 4, as we have 4 comparators, this is taken as V by 4, 2V by 4, and 3V by 4 respectively. So as you can see here, we have constructed a table looking at the picture, and V reference, which is given to the inverting terminal, is always started with 0. So we can infer that the non-inverting terminal starting from x0 is always higher than the inverting terminal, right? So what we have is, here we have taken the x3, x2, x1, and x0. From the first, we have 0, 000, and 1, that 1 for x0. So what happens here? Always the non-inverting terminal is dominating, which means that output of the comparator is becoming 1 at every stage. At the end of when we reach fourth comparator, all the outputs is all 1, right? The output is all 1, and it is being given to the priority encoder in order to encode it to the digital signal. So here the conversion of analog to digital using comparators, and this is very simple as well. So This is the overall thing about the flash comparators. Let us look into the advantages and disadvantage. The advantages is, no, I've told you in the beginning itself that it is a required. We use this ADC where the speed is a main requirement for it. But disadvantage is that there are more number of comparators which are required, which may take more number of which can increase the cost as well. So these are the advantage and disadvantage for the flash comparator. So the next type of comparator is called as the successive approximation, ADC. The successive approximation ADC is the most modern ADC integrated circuit, and it is much faster than the dual slope, which will be seeing it in the further slides, and the flash ADC, since it uses a digital logic that converges the analog input voltage to the closest value. So when we look at the diagram of the successive approximation ADC, we see that we use a successive approximation register for storing the output of the comparator, and we use a digital to analog converter, which is a 4-bit, and a 4-bit latch which is being used, and from there we get the digital output. We see that the analog input is being given to the inverting terminal, and the non-inverting terminal is given to the output of the DAC. So always while solving in this type of comparator, we take the values of B3, B2, B1 and B0 to be as 1,000, that is 1000. From that we keep on comparing the values of the input voltage to the output voltage of DAC, right? So input voltage may be anything depending upon what is that. We cannot say let's say it is 11.5, 12.5, it can be anything, right? So it keeps on comparing with the output of the DAC. So I have what you can call here is that I have the overall diagram that gives you the complete information of the comparison. Here also they have taken the as 100. The binary number of 100 is nothing but 8, right? So if V input voltage to the comparator is greater than the input voltage from the the DAC is greater, then you can observe here that the most significant bit remains as it is, and the next bit is changing to 1. This condition is only possible when V in is greater than VA, that is the output voltage from the DAC. What if in the case of V output of the DAC is greater than V in? Then the most significant bit is reset to 1, and the next significant bit is changed to most significant bit is changed to 0, and the next bit is changed to 1. As you can see here, and the top part is always, the condition is always taken as V in is greater than VA, which means the output of the DAC, and the below one is the vice versa. And let us go further in it. When we take 1100 of the top, if V in is greater than VA, then what happens is that 1100, right? You can 1110, 1110. But in the case of V output is less, V input, voltage input is less than the voltage of the output of the DAC, then we have 1010. Is that when V input is always greater than the when the non-inverting terminal is greater than the non-inverting terminal, then it shifts to the next, it shifts to the next bit and changes to 0. In the case of the opposite one, it resets the current bit position to 0 and converts the next position to 1. So this is the overall combination. So when we start with 8, depending upon the input, the reference voltage, it can be either V input is greater, or V input is less than the voltage output of the DAC. So this is nothing but the overall concept of successive approximation DAC. Okay, these all the values here shown here are the possible digital signal outcomes. And here also we have an advantage of this, that it is good speed, resolution, right? But it's less accurate. We can say that it's less accurate. So for accuracy, we look into the next type of ADC called as dual slope ADC. Dual slope ADC is a converter that the comparison of the voltage is generated by using an integrated circuit. Here, the capacitor, you can see here the first comparator with the capacitor over it. This portion is called as the integrator, and the next the comparator is called as the, it is for comparing the input voltage with the uh, input voltage with the ground, you can see here. So what happens here is that I have to tell you here that VA and V reference. Okay, as you can see here, the starting point of the right side of the diagram, it is always in the opposite polarity. V reference is always in the negative side and VA is on the positive side. And we come further, we have an AND gate where the one input is given by the output of the comparator, and other input is the output of the clock. The output of the clock is always assumed to be as high or 1, and it depends on the output of the comparator whether the AND gate is activated or not. The output of the AND gate is given to the binary counter. So it is clear that binary counter is activated only if the AND gate's output is 1, right? AND gate's output is 1. From the binary counter is given to the output latch, from which we get the digital output. Here we have charging and discharging of capacitor, which will determine the input of the comparator and also the output of the comparator. When we see the graph here, we can see that the upward graph is showing the charging of the capacitor, and the downward graph is showing the discharging of the capacitor. Say we have taken capital T for the time of charging and Tx for the time of discharging. For T, we have the formula as V reference by RC. Okay, V reference by RC into Tx. So V reference is nothing but the reference voltage which is being given, and R and C are the values of the resistors, which can be seen over here in the integrator part itself. Okay, in the integrated parts itself. So this is nothing but dual slope ADC. And one more thing, and the name is dual slope because we have charging and discharging of capacitor. There are two slopes. There are two slopes like this, and hence the name. So we have advantages and disadvantages of here itself, and these are the notes which are for your reference. If you want it, you can refer it to it by pausing the video. The advantage is nothing but it's it's very accurate. This type of ADC is used where accuracy is more prominent than the speed. Example, multimeters. A clear-cut example is a multimeter where we require more accurate value rather than a speedy output. And disadvantage is that charging and discharging of the capacitors takes a very long time. In the graph, you may have seen a small time, but in the practical world, it takes quite a long time than other ADCs. Okay, so next a type of ADC is called as the pipelined ADC. So in this type of pipeline ADC, the overall strategy here is to break down the overall conversion of analog to digital is being broken down into a sequence of n serial subtasks. There is nothing but you can see the stages in the diagram which has been mentioned over there. Right, then in a pipeline ADC we can have a resolution from varying ranges from 8-bit to 16-bit. We have those ranges as we can see here. So there are multiple stages, and we use here a 3-bit DAC with use a 3-bit ADC, and the sigma symbol which you can be seeing at the top of the diagram is nothing but subtractor, which I will be telling you the use of that thing. Okay, then we have an error detection and correction circuit from the bottom where we receive the digital circuit. So when we look at the stages, we have multiple stages. In the first stage, the input voltage is being sampled, and it is being digitized using a k-bit DAC, analog to digital converter. It is being digitized, and we use a subtractor to subtract the difference of the input voltage, and then we use a RA circuit to create the output for the next stage. So this is the overall concept, that in each and every stage this is the operation which will be followed. Okay, in the next stage, as you can see here, the sample of the incoming residue, the input is the output of the previous stage, right? So once it has passed the input, it is immediately ready for taking the or accepting next set of inputs. And at every stage, you can see here, we have the sampling function which is being performed. So we have a higher sampling rate, higher frequency, so that the reconstructed digital value, or the construction of the analog reconstructed wave, is more accurate. Hence we use these kind of pipeline ADC for a more accurate, as we use in the previous analog to digital converter. So the overall idea here of the pipeline ADC is to cascade several low, as you can see here, several low resolution stages to obtain a overall higher resolution stages. So next we'll be doing the performance of the performance which are affecting the analog to digital converters. So the first type of the first performance parameter is nothing but the offset error. So offset error, as you can know, we can define it as the actual difference between the actual and the ideal, the ideal ADC curve in the first transition voltage, as it described in the figure. This we can see that we can see this offset error, we can compare to the same we can compare it to the same as that of the zero scale error. Ideally, when the analog input is between 0.5 to 1.5 lsb, the digital output should be ideally still until the first transition occurs at 0.5 lsb. As you can know, in the vernier calipers and all, we have that zero scale error. When we try to exactly coincide with the zero value, it does not, there is some error. So this is the same kind of error which can be seen in the ADC. The ideal ADC curve is a straight linear line, okay, which I have represented in the left diagram, which if you can observe. But due to some error, there is a but due to some error, we can say that the resolution of this is infinity. That is only the theoretical concept, but in practically we should obtain a curve or a graph which is in the manner of a staircase, which you can see here. The width of the staircase, or you can say that in the x-axis, can be of 0.5 to 1 bit or 1.5. Okay, here in the offset error, the position of the staircase curve shifts either to the right or to the left, depending upon the type of ADC, due to some technical issues, like it may be the manufacturing of the circuitry, or it can be the electrical glitches which can occur over here. So there are two offset errors which can be seen over here, that is positive offset error and negative offset error. Positive offset error is nothing but when the shifted the shifted ADC curve is above the perfect ADC, which can be seen in the right diagram. And if you see in the left diagram, the staircase can be seen in the right side, which is below the perfect ADC. This is called as the what you can see that this is called as the negative offset error. Okay, yeah. So actually, the in this another concept, another formula is there which I forgot to give you. That is nothing but the offset error in voltage can be calculated by the V reference into you can say that the error in LSB by 2 to the power of n. So I'll repeat it again. It is a V reference into error in the least significant bit by 2 to the power of n. So this n is nothing but the n-bit ADC. It can be a 2-bit ADC or 4-bit ADC. So next, moving on to the next performance parameter, that is nothing but the gain error parameter. So the gain error is nothing but it is defined as the deviation of the actual transition. Right, you can see here that the actual ADC curve has been is changing here. Okay, is changing from the perfect or the ideal curve. In this, we have two types of representation, that is positive representation and the negative representation. The negative representation is shown in the left diagram, where we can see that there is a decrease, or it is below the ideal curve, ideal straight line, by a difference of 0.5 lsb, 0.5 lsb. But in the same, the actual ADC curve is 1.5 above, plus 1.5, that is above the ideal ADC curve. Okay, this as you can see here, this transition represents the difference between the ideal and the actual slope of the ADC's curve. See, this is nothing but the it represents the difference between the you can say that the ideal voltage at which converter provides full scale output voltage to the actual voltage which is being given to the converter at that point, right? So let us move on to the next type of parameter which affects the ADC. So the differential linearity error can be defined as the maximum deviation between the actual and the ideal steps. Let us understanding it a simpler way. So this is nothing but the difference between the ideal curve and the actual curve. As you can see in this left side diagram, there is a difference of zero point 0.6. It's a varying differences. It's not a perfect staircase diagram, but there is no the difference is much higher at one point. The difference is much lower than a point. It is you can see plus 0.6 LSB at one type, and other places you can see minus 0.5 LSB. Okay, so we can just say that it is a difference between the actual curve and the ideal curve. Okay, but in the once we have a look at the in the right diagram here, if the difference is zero, so let me take an example. Let me take as that the ideal LSB is 1 and the actual LSB is 1.5. So we do the subtraction like actual minus ideal, right? So we get the result as 0.5 in this case, in the example which I have taken. But what if the difference is zero? If the difference is zero, then whatever the input, that corresponding output, that means the corresponding output code which is being to that point will be missing. So if they have taken I have taken example here, saying that at 101 point the this is missing. Okay, what you can say that so the difference between the actual curve and the ideal curve is zero, then irrespective of the input, that corresponding binary output will never occur, right? This is nothing but the differential linearity error. Hope you understand. Yeah. So the next type of parameter let us see is that it is a integral non-linearity error. See, this is a simple one actually. There's no much there's nothing. Oh, just a minute. Sorry. There's nothing but here. Let us go back to a minute. So we can see here that the integral nonlinearity error is just a parameter to determine the performance of the ADC, as I have mentioned earlier itself. Basically, the distribution of DNL points will be determining the total INL error, right? The maximum INL error may be higher or lower than the DNL. So from this we can infer that the DNL is the basis of finding out. For us, it's a basis for finding the INL error, that is the integral nonlinear error. So in order to find out this integral nonlinear error, we are having two methods. One is the endpoint method, the other one is the best fit method. Okay, so let us go to the endpoint method. Endpoint method is very simple. It's nothing but a straight line which is joining the two endpoints of the actual transfer curve. Okay, that if you see in the diagram, the white continuous line is representing the ATC. And another observation you can have, you could have made that it is always passing through the origin of the axis. So we have to draw a line, the ideal transfer line, such that it is passing through the two end points of the actual transfer curve. Okay, this is nothing but the the endpoint method. Simple as that. Endpoint method is that end points. So the end point of the actual transfer curve is taken, and a line is joined passing through those two points. And we can say that this is more accurate than the next method, that is the best fit method. Right? This is the best fit method. In the best fit method, we have what do you call? In this method, you can see the actual transfer curve. We draw a line, a linear line, such that it is almost plus or minus close to the the actual transfer curve. We draw an ITC such that it is almost close to the ATC. So from this, the INL error can be calculated from both of them. The difference, you can see that the difference between the actual transfer curve and the ideal transfer curve is it is the best method, so that you can get a more accurate error in more accurate error, so that we can keep going on or keep designing a more better performing ADC, right? So so next, I will be talking about a single and a very simple application that we use it in our everyday life, and that is becoming a more advanced. It is becoming more advanced day by day. So the application is nothing but the ADC in telephone. As you have all used telephones, ADC is used in it. How? When you take the landline or the telephone, you have two devices at the receiving as well as the speaking end. One, you have the speaker, and other you have the microphone. At the microphone, we have not we are not, as we are speaking, our wave is going and hitting the device. But this wave, as you know, it is not a digital form. We're not passing any we are not telling 1001324 100012010 like that, but we are giving an analog signal. Our analog signal is nothing but the sound wave. So here, ADC plays a very important role in converting the analog signal to digital signal, right? Because otherwise it is not converted. That our voice is not transmitted. Our voice is never transmitted. It should be always transmitted in digital form. So that is the main theme which have been provided in the PPT. For plain ordinary telephone service, such as provided by the landline, analog signal is converted by a microphone in an analog electrical signal. This electrical signal is transmitted through a copper cable and to the telephone company's central office. And this is nothing but the basic information which have been given, that this only digital signal is being transmitted to the central telephone office. Okay, in telephones, usually we have seen through a lot of the ADC converters. In that, usually ADCs or flash type ADC or dual type ADC is used because for accuracy, right? Accuracy as well as speed also. There is when we talk, our voice hits the a device, and it passes through the anti-aliasing filter, so that all the other high frequencies and unwanted frequency is getting filtered over here, and then it passes through the ADC, where a flash type or dual slope ADC is used in order to convert our signal into an output digital signal. This digital signal passes on to the central communication, central exchange, telephone exchange, where from that it is being transferred to the receiver end, right? It is being transferred to the receiver end, which have been shown, which I have shown over here. See, which is transferred to the receiver end. In that receiver end, he cannot hear the digital signal, so again it has to be converted from digital to analog converter, right? So analog signal is what we give, and the circuitry only understands, the electronic circuitry only understands the digital signals, right? The overall structure have been provided in these 8 points, which is very simple. As you can know, I've already explained that when you call, you speak, right? The microphone or the mouthpiece is a transducer. Transducer is nothing but the conversion of that is a whole overall piece, where it consists of anti-aliasing filters and ADCs and all, right? Yeah. And our analog signal is nothing but the waves. Yes. And you can see that at the speaker, the sound wave is being converted to the electric wave, so that we hear it, right? Yeah. So, and this is the overall structure of details about analog to digital converters, and hope you understood all of the things and got an overall understanding of what is ADC and where ADC can be used, is what I have tried my level to make you understand. Thank you.